Okay, so last time we were looking at some properties and formulas associated with logarithms. So we'll continue with that. So what we'll do is how to look at how to do differentiation of logarithmic functions. Okay, so if I have, say, a function f of n, and you have log of f of n to the base e. So we will work with base e, but if you also have some other base, we'll see how to convert it to base e and then do the differentiation. So in order to differentiate log function, you have to have base e. So that's the first thing you have to remember. So if you don't have to the base e, you cannot differentiate a logarithmic function. And so now here, the formula for differentiating a function f of n, or log f of n to the base e, is this: 1 over f of n, then differentiation of the function f of n with respect to n. So for example, if you have f of n to be n itself, then log n to the base e, you're differentiating with respect to n. So that is 1 over f of n, so f of n is n, so 1 over n, then differentiation of f of n with respect to n, so differentiation of n with respect to n, which is 1, so the answer is 1 over 1, n. Now if you have f of n is n square, log n squared to the base e, differentiation with respect to n, is 1 over f of n, which is 1 over n square. Differentiation of n square with respect to n is 2n. Now if you so 2n over n square, which is 2 over n. So what I was supposed to say is a formula like this. So if you have, say, what do you call, n to the power k, and differentiation with respect to n, the formula is k times n to the rise to k minus 1, and differentiation of n with respect to n. So differentiation of n with respect to n is of course 1, that's why we simply leave it like this. Okay, so you can take it up as a formula. I think you might have seen this in a calculus class. So for example, if you have n rise to 4, differentiation with respect to n, the answer is 4 times n rise to 4 minus 1, which is 3. Okay, any questions so far? Good, so let us continue. So what we were looking at in a broader picture is this limit approach. So if you have two functions, f of n and g of n, how to decide which function grows faster than the other, or whether they are growing at the same rate. So that's what we are going to do now. So we are given two functions, log n and square root of n. So f of n is log n to the base 2. So again, remember, this is not base e, this is base 2. Log n to the base 2, and g of n is square root of n. We want to decide which of these two functions grows the same faster, or whether they grow at the same rate. Okay, so we are going to find limit n tends to infinity f of n over g of n. And let us substitute the two functions and see what happens. So log n to the base 2 square root of n tends to infinity. Now if we substitute the limit value n equals infinity, log infinity will be infinity, square root of n, so square root of infinity is also infinity. So you have like infinity over infinity, which is not defined. So in a math class, we should have seen what is called as L'Hopital's rule that can be used to handle such scenarios. So when you apply the limit for the two functions, and if you either get infinity over infinity, or 0 over infinity, infinity over 0, so if you have any of these format, then for any of these result, then you have to apply L'Hopital's rule, because there's no finite answer for these things. So here we have infinity over infinity, so which is not defined, so we have to apply this rule, and this rule is stated here. So f of n over g of n limit n tends to infinity is same as f prime of n over g prime of n limit n tends to infinity. And what is f prime of n is just nothing but the differentiation of f of n with respect to n is represented as f prime of n. Similarly, g prime of n is differentiation of g of n with respect to n. So in this case, these are our f of n and g of n, so we have to differentiate these two functions. Let us do one by one. So f prime of n is differentiation of log n to the base 2, that's our f of n with respect to n. Now remember I said you can do the differentiation of a log function only if the log function is to the base e. But here we have log to the base 2. So what we have to do is first transform this to something that involves base e. And last class we saw a formula. If you have any base like b, log n to the base b can be written as log n to the base e divided by log b to the base e. So basically you have to the base e, and this n goes to the numerator and this b goes to the denominator, and you have base e in both numerator and denominator. And this is what we are going to do. Log n to the base 2 is log n to the base e divided by log 2 to the base e. Now if you think about this, log 2 to the base e is primarily a constant because 2 is a constant, e is a constant. So log 2 to the base e is going to be a constant. So you can take this outside, so this is the denominator, so 1 over log 2 to the base e, and differentiation of log n to the base e with respect to n. Now how would you differentiate log n to the base e with respect to n? We saw this earlier today. So that is 1 over n differentiation of n with respect to n. So n is our f of n. So 1 over f of n differentiation of f of n with respect to n is simply 1 over n. And that's what we have here. So log 1 over log 2 to the base e times 1 over n, and both on the denominators. I'm just combining these two together. Okay, so I hope this is clear. So basically you have to first transform this to the base e, log to the base e, and then apply the formula for differentiating a log function of f of n. Now for g prime of n, g of n is square root of n. So differentiation of square root of n with respect to n, we can use the formula that I mentioned here. So here k is half. So that is going to be then half times n raised to half minus 1. And that's what I have written here. So half times n raised to half minus 1. K times n raised to k minus 1. Now half minus 1 is negative half. So is n raised to negative half in the numerator, so I can bring it down, so that will be n raised to positive half. Okay, so 1 over 2 n raised to negative half becomes 1 over 2 n raised to positive half in the denominator. So now you can put these two things together. So f prime of n is 1 over n log 2 to the base e that we got for f prime of n, and then g prime of n is 1 over 2 n over half. Now all you have to just simplify this. So again, log 2 to the base e is a constant, 2 is a constant, so this is 1 over half. So if you kind of bring this half to the numerator, it becomes 2, and this is 2 over log 2 to the base e, and again 1 over n raised to half. If you bring it to the numerator, it becomes n raised to half divided by n. So now this thing is going to be n raised to half divided by n is simply 1 over n raised to half. So it's just math here. The 2 over log 2 to the base e is a constant, so we can keep it as it is. So n raised to half divided by n is nothing but n raised to half minus 1 right? So that is n raised to negative half, and that is 1 over n raised to half. So 1 over n raised to half, if I apply the limit n tends to infinity, the denominator becomes 0. So 1 over infinity, sorry, not the denominator doesn't become 0, 1 over infinity, so 1 over infinity, I put in INF for infinity, so 1 over infinity is 0. So it's going to be 2 over log 2 to the base e times 0. So this n term will evaluate to 0. So that's the whole thing is 0. So we basically have what? Limit f prime of n over g prime of n as n tends to infinity is 0. And that, according to L'Hopital's rule, is same as f of n over g of n limit n tends to infinity. So we have f of n over g of n equal as n tends to infinity as 0. That means we have to decide whether they grow at the same rate or at a different rate. Now if they grow at the same rate, we saw in the list of formula that t of n over g of n, in this case f of n over g of n, limit n tends to infinity should be a constant. So it's very clear that, and it's a constant other than 0. So we did not get a constant other than 0, we got 0. So if we got 0, that means one of them is growing at a faster rate. So we have to decide which one grows at a faster rate. So if we get 0, that means the denominator is a larger value compared to the numerator. So it's like the numerator divided by a very large value only will tend to 0. That means a g of n function, the denominator function, grows faster than the numerator function. So once we decide that it is like they are growing at a different rate, we have to use the big O notation. Now what goes inside the big O notation? Always the faster growing function. So the faster growing function is the denominator function, which is g of n. So f of n on the left hand side equals big O of g of n. So the denominator is growing faster. So f of n is big O of g of n. So that means log n to the base 2 is big O of square root of n. That's the final answer. Now if you look at it, you see that means, from the definition of big O notation, the f of n function on the left hand side grows at a rate less than or equal to the function inside the big O notation. That's what big O notation means. That means the log n function grows at this rate less than or equal to square root of n. They are not equal because they are two different functions. So that means it grows less than square root of n. So that means what? Log n function is pretty slow function. We saw earlier that log n grows slower than n, and now we see it grows even slower than square root of n. Now for practice, you could try comparing log n again to the base 2 with, say, n raised to 1 over 100. So we saw n raised to 1 over 2, that is square root of n, right? N raised to 1 over 2 square root of n. So instead of 2, you could try n raised to 1 over 100. So it will look like n raised to 1 over 100 is a very small slope function. Yes, but if you go through the same approach, you will see that log n is actually equal to big O of this function. So that means log n grows even slower than n raised to anything like 1 over 100 or 1 over 1000, any such function. So that's the power of log functions. They are very slow growing functions. Okay. Any question so far? Okay, good. So okay, I can continue for another example and then we'll stop it. Okay, so let us look at one more example and then we will go to the next topic. So let us say you are given two functions, f of n and g of n, both involving logarithms. So log square n and this is log n square. Now if you have to look at this very carefully, they are two different functions, they are not the same. log square n is same as like a square. So we say a square is what? So when I say a square, it means a times a. So like that, log square n is log n times log n. That's what log square n is. Whereas log n square is like this. So log of n square. Now we know n square is n times n. N square is n times n. So log of n times n is like what? Log n plus log n. So last time we saw a logarithm formula. Log p times q, any base, doesn't matter what base it is log p to that particular base plus log q to that base. So that's what we're going to use here. Log n times n is log n plus log n. So that is 2 log n. Log n plus log n is 2 log n. It's like a plus a is 2a. So basically we have f of n is log n times log n, and g of n is log n plus log n, which is 2 log n. So let us put them together. So f of n the numerator, g of n the denominator, and you apply the limit n equals infinity, we again get infinity over infinity. Right? So, one second. Okay, I'm sorry. Log n times log n, okay, that is f of n, divided by 2 times log n. We can simplify this right away here. Log n and this log n will cancel out. Okay, so that is then going to be equal to log n over 2. Log n over 2. Now we apply n equals infinity. So 2 is a constant, but log of infinity is infinity. So infinity over 2 is infinity. So this means, so you have two functions, f of n over g of n, and the ratio has come out to be infinity. That means they are not growing the same rate. It's not a constant other than 0. It's infinity. So it means we have to use a big O notation. And which of the two functions grows faster? That's what we have to decide. So when you get the ratio as infinity, that means the numerator is much larger than the denominator. That's why you get to be infinity. If the denominator is much larger than the numerator, we would get like what we got here, 0. Whereas here we get the infinity means the numerator is much larger than the denominator. So right away you can decide the numerator function, the larger function, goes inside the big O notation, and the other function goes on the left hand side. So g of n equals big O of f of n, because f of n grows faster than g of n. So now you plug in the two functions. Log n square is g of n equals big O of log square n. So again, you see here, this is like a log function, and it grows less than log square function. That's how you have to interpret. So that means you can also again have here, instead of n square, n raised to 100. So log of n raised to 100 is going to be, anyone can say what is n log of n raised to 100? Log n square, I said, is 2 log n. So log n raised to 100 is going to be 100 times log n. So instead of 2, you are going to have 100 times log n. So that's going to be again going to be log n over 100. Now we apply the limit n equals infinity. It's going to be log infinity over 100. That is going to be still infinity. That means we are going to have still log n square is smaller than log n to the power 100 to be smaller than log square n. Okay, so like this problem here, it doesn't matter whether it's square root of n or n raised to 1 over 100. That goes inside the big O notation, of course, in this case. But in this case, we are taking the logarithm of that. So once you take the logarithm of that, that becomes a slow growing function. So log n square, log n raised to 100, anything is going to be less than log square of that. Okay. Okay. Any question so far on these problems?